This is the introduction to quantum mechanics part 3. So in order for electronic diffraction to occur, the distance between these slits or atoms the atoms of the diffracting barrier must be on the order of the same size of lambda, the wavelength of the electron. So again, the wavelength, as discussed previously, is the distance from crest to crest, right, of the wave, right? And for diffraction to occur, we knew already previously from classical wave theory that the distance between the slits must be on the order of lambda. It doesn't have to be exactly the same, but it has to be close, right? So let's take a look at the conditions under which that might occur. So Louis de Broglie hypothesized in his PhD thesis that, and it was several years earlier before the Davison and Germer experiment, that lambda is equal to h over p. And we know that momentum is equal to mass times velocity. So we'll make that substitution there, right? Where the velocity is the velocity of the electron. The velocity of the electron approaching the slits, right? Or in this case, the velocity of the wave function approaching the slits. So, so we need to find this velocity. First thing we notice that if the velocity is very big, then the wavelength is very short, because if this number is very big down here, then it divides Planck's constant. Planck's constant is 6.626 times 10 to the minus 34 joule seconds. So it's already a small number, but this mass of the electron is 9.11 times 10 to the minus 31 kilograms. And then the velocity is a number that is usually some order of magnitude much larger than those numbers. In this case, it'll be about 10 to the 6th meters per second. So let's calculate what the velocity would be for the Davison-Germer experiment in 1927. So they used an accelerating potential difference of 54 volts to accelerate the electron out of the gun, right? We'll assume that the electron, when boiled off of the coil, we'll assume that the energy of the electron being boiled off of the coil is negligible compared to the amount of energy added to it due to that accelerating potential. Now the energy added, which we'll call the work, is equal to Q times delta V, right? And they were using a potential difference of 54 volts, so we know that number. So we're going to neglect the initial energy of the electron coming off of the coil, and then the energy added will be Q times delta V, where Q is the charge of one electron, which is 1.602 times 10 to the minus 19 coulombs. That number was known at the time. And then the final energy, the energy of the electron coming out of the gun, is just the kinetic energy of the electron. And we knew then and we know now that the kinetic energy of a particle is equal to 1/2 mv squared, where m is the mass of the particle, right? So we'll solve for the velocity of the electron, and we'll get the velocity is equal to the square root of 2q delta v divided by, and this is a potential, I'll put these little hats on it to annotate that, divided by m. It's the square root of all of that, right? And if we calculate this number, we will get 4.36 times 10 to the 6th meters per second. So that is the velocity of the electron, right? Okay, we'll put this right here. Okay, then back to de Broglie. Lambda is equal to h over mv. H is Planck's constant, 6.626 times 10 to the minus 34. Divided by, and this is a 4. Let me put that, yeah. Divided by the mass, 9.11 times 10 to the minus 31 times the velocity, which we just calculated, 4.36 times 10 to the 6th. And if we calculate this number, we will get 1.65 angstroms for the wavelength. Now, Davison and Germer, after they had achieved the electronic diffraction, which they did accidentally, by the way, they initially did not notice electronic diffraction, but then they accidentally oxidized their sample, and then when they had to heat it, when they heated it to remove the oxidation, the nickel target crystallized into this perfect arrangement such that the distance between the atoms was about equal to this. And whenever they used X-ray diffraction techniques to determine what the distance in between the nickel atoms was, and they found that the distance was about equal to 1.67 angstroms, which was in very good agreement with de Broglie's wavelength. And so electron diffraction was observed for the first time. So the reason it had not been observed up until that time is because these are staggeringly small numbers, and angstrom is 10 to the minus 10 meters, and so it was very, very, very small, and it just simply had not been observed with any of the technologies previous to 1927. Okay, and then in 1927 it was observed accidentally. So now we're going to move on from electrons, and we're going to do an experiment with photons and see how photons line up with the quantum theory, because we've all been told in grade school or somewhere along the line that light is made up of these particles called photons. So let's see how they behave according to this model of nature. So we have a laser here. It's a red laser and a red laser has a wavelength of about 650 nanometers. That's nano is 10 to the minus 9, so 650 times 10 to the minus 9 meters. And we have a barrier, right? And the quantum mechanical wave function, right? Now we're not describing this in terms of an electromagnetic wave anymore. We're using quantum mechanical wave function to describe it, to see if we can use quantum mechanics to describe this experiment instead of using the previous electromagnetic wave theory. And so we can, and if we, just as before, if we describe each individual photon, leaving the source as not as a particle, but as a wave of potential, a wave of possibility, a wave function that conveys all information about the particle, and that wave function approaches the slits, then the wave function will diffract through the slits if the slit distance is on the order of the same wavelength as the wave function. And these two new sources, both associated with the same photon, because wave functions only interfere with themselves. They do not interfere with other wave functions, right? Those two wave functions interfere with themselves to arrive at the back, giving a probability distribution of where the photons might occur. And it's as before, we see the standard interference pattern that we've seen in previous experiments, previous thought experiments that we did in the intro part 1 and the intro part 2. So we see that the quantum theory is perfectly capable of describing photons. It's also capable of describing electrons and any given particle in nature that we've discovered so far. The electromagnetic wave theory was first put forward by James Clerk Maxwell and was successful for many years until Heinrich Hertz came along and did an experiment with light and electrons. He shined light on metal, right, and ejected electrons from the surface. And this is called the photoelectric effect experiment. And it was first performed by Heinrich Hertz, but not explained. It wasn't explained until several years later in 1905 by Albert Einstein, right, where he hypothesized that light came in the form of a packet of energy called a photon, and the quantum theory was thus born in that experiment, or in the explanation of that experiment, rather. So the quantum mechanical wave theory fails in the photoelectric effect, right? It's not adequate to describe what's going on in that experiment, because if you have a large intensity, right, then you should eject, more and more electrons. But that was not observed. It was observed that, and the intensity is proportional to the amplitude of the wave. It was observed, rather, that the energy that the electrons were ejected off of the surface of the metal with was proportional to the frequency, not to the wavelength of the light. Excuse me, not the wavelength of the light, the amplitude of the light, right? Because wavelength and frequency are directly related. C equals lambda F. But so the electromagnetic wave theory failed in the photoelectric effect, right? It was useful to explain this experiment, and still is. But the quantum mechanical wave theory explains both the photoelectric effect and the double slit experiment, right? And so we always want the most simplest model of nature, and so we choose to go with the quantum mechanical wave theory of particles, right? And so the most recent big picture is a subject called quantum electrodynamics, which is the using James Clerk Maxwell's equations to quantize the fields, right, to give a full picture of what's going on, right? But quantum mechanics is necessary to describe nature fully. So I'm going to step aside and give you a clear screenshot. That is it for part 3. Moving on.